I've started with discussion on radiation, and in my previous lecture I've discussed what is a black body, and I was discussing what are the properties of a black body. So in continuation of that lecture, let me again go revisit the properties of the black body radiation. The last property that I had discussed in the last lecture was that as the temperature of a black body increases, the peak of the black body spectrum shifts from the infrared region towards the high frequencies, that is the visible light region. Next property. Since there are infinite number of modes, which implies infinite heat capacity, that is infinite energy at any non-zero temperature, as well as an unphysical spectrum of emitted radiation that grows without bound with increasing frequency, a problem known as ultraviolet catastrophe can also be seen in the black body spectrum. The phenomena of ultraviolet catastrophe will be dealt in detail when I discuss the Rayleigh-Jeans law. Next property. In quantum theory, the occupation numbers of the modes are quantized, cutting off the spectrum at high frequency in agreement with the experimental observations and resolving the catastrophe. The study of the laws of the black bodies and the failure of the classical physics to describe them establishes the foundations of quantum mechanics. That is to say that ultraviolet catastrophe is the major reason why the quantum theory gained precedence in discussing the black body spectrum. A perfectly insulated enclosure that is in thermal equilibrium contains black body radiation and will emit it through a hole made in its wall, provided the hole is small enough to have a negligible effect upon the equilibrium. That is to say that radiation is emitted in such a way that the temperature of the black body does not change. Now, why is it not possible to see the black body radiation at ordinary temperatures? A black body at room temperature appears black. Why? Because most of the energy it radiates is in the infrared spectrum and cannot be observed by the human eye. The human eye can only see the visible spectrum. Since the human eye cannot identify light waves below the visible frequency, a black body viewed in the dark at the lowest just slightly visible temperature subjectively appears grey in color. When it becomes a little hotter, that is, if the temperature of the black body is raised, is increased, it appears dull red. If the temperature is increased further, it becomes yellow, then it becomes white, and ultimately blue-white, which is the hottest. Black holes are near perfect black bodies in the sense that they absorb all the radiation that falls on them. It has been proposed that they emit black body radiation called the Hawking radiation with the temperature that depends on the mass of the black hole. This is from the work of Stephen Hawking. Now here I am showing you a black body spectrum. As you can see, on the x-axis we have the wavelength, on the y-axis we have the intensity. So when the wavelength starts increasing from 0, then what is happening is that the intensity is showing an increase. It reaches a maximum, shows a peak, and then it starts decreasing with further increase in wavelength. This spectrum is shown for three temperatures: 6000, 4000 and 3000, 2000. You can see the peak is shifting to a lower value if the temperature is decreasing. Also, the three parts of the spectrum pertaining to different wavelength ranges is also shown in the figure. We have the ultraviolet region, we have the visible light, and then we have the infrared part of the spectrum. The first faint glow appears as grey. The visible light is actually red, but the low intensity light activates only the eye's grey level sensors. With the rising temperature, this glow becomes visible even when there is some background surrounding light, first as dull red, then yellow, and eventually a dazzling bluish white as the temperature increases. When the body appears white, it is emitting a significant fraction of its energy as ultraviolet radiation. The sun, with an effective temperature of approximately 5800 Kelvin, is an approximate black body with an emission spectrum peaked in the central yellow-green part of the visible spectrum, but with significant power in the ultraviolet as well. Because the temperature of sun is very high, therefore the spectrum is also the way I have just mentioned. The black body radiation provides an understanding into the thermodynamic equilibrium state of the cavity radiation also. An object that absorbs all radiation falling on it at all wavelengths is called a black body, as I have mentioned in the beginning of the lecture. When a black body is at a uniform temperature, its emission has a characteristic frequency distribution, or we can say wavelength distribution, that depends solely on the temperature of the black body. This emission is called the black body radiation. A black body radiates energy at all frequencies, but its intensity rapidly tends to zero at high frequencies, that is short wavelengths. For example, a black body at the room temperature, that is 300 Kelvin, with 1 square meter of surface area will emit a photon in the visible range 390 to 750 nanometers, that is 10 to the power -9 meters. For most practical purposes, such a black body does not emit in the visible range. The black body law may be used to estimate the temperature of a planet orbiting the sun also. So, this is the application of the black body laws which we will be studying shortly. No body in actual practice can be perfectly black, as I have mentioned before. The nearest examples of ideal black bodies are lamp black and platinum black. They absorb visible and near infrared radiation, but cannot absorb far infrared radiation. Now, let me discuss a black body that was constructed. It is called the Ferri's black body. I will be shortly showing you the figure also. What is this black body and how does it work like a black body? The Ferri's black body consists of a double-walled hollow metal sphere having a small aperture and a conical projection opposite to it. The inner surface of this hollow metal sphere is coated with lamp black, and the outer surface is nickel polished. The space between the sphere is evacuated. The radiant energy entering the aperture suffers multiple reflections and get 98% absorbed at each reflection. Why? because the metal sphere is coated with lamp black. When the sphere, double walled sphere, is heated to a certain high temperature, the radiation corresponding to that temperature is emitted from the aperture. Thus, the aperture acts as a perfect black body. Here you can see the figure of the Ferri's black body. You can see we have the double walled hollow metal sphere. The space between them is evacuated. On the right hand side, you can see the aperture. Through the aperture, radiation is incident and enters the metal sphere. The outer wall of the metal sphere is nickel polished. Just opposite the aperture, you have the conical projection, as can be seen on the left hand side of the figure. Now, the light, when it enters through the aperture, falls on the conical aperture projection, and it falls at different parts of the metal sphere. Why do we take a conical projection? Because if we take a conical projection, then the incident radiation that is incident and that enters the metal sphere will not be able to leave the metal sphere, because that is the basic condition of a black body, that whatever radiation falls into it has to stay into it, that is, has to be absorbed into it. Therefore, this is how Ferri designed this black body. It was a brilliant fabrication, I would say, because to think of that we can place a conical projection just opposite the aperture to avert the problem of the light entering the black body, leaving it immediately, was averted. Now, I have discussed what is a black body, I have discussed the properties of a black body, I have discussed the spectrum of a black body. Now, let me discuss what is the relation between the emissive power of a surface and energy density of radiation emitted by it. Look, energy is emitted from a black body, from the surface of a black body. Now, this emission can either take place normal from the surface, or it can take place at any angle from the surface. So, let us take the simple case first. Let us assume that any emission from a black body is normal radiation. To expand further, let us assume that the surface AB of the black body of area S emits normal radiation of energy density U. Then the emissive power E of this black body, which is represented by the surface area AB, will be given by U into S into C by S, which is equal to UC, where C is the speed of light. Now, you have to appreciate why have I written USC. U is the energy density. It means it is energy over volume. We want to calculate the energy. So, this volume has to be negated. How to negate it? If you multiply by surface S area, area is meter square. So, 1 meter square will cut with the meter cube or occurring in the denominator of U, and I am left with only meter. Then I have multiplied it with C. C is meter per second. So, that meter again gets cancelled and we are left with energy density by C, and because we have to calculate per unit area, so I divide it further by S and I get E is equal to UC. Very, very important formula. Thus, we can say that in a nutshell, if surface emits radiation only in a direction normal to the surface, the emissive power of the surface is equal to the product of the energy density of radiation and the speed of light. Next, let us find out the relation between the emissive power of a surface and energy density of radiation emitted by it if this emission is taking place in all directions, all possible directions. To derive this, let us say that the radiation is occurring only at a particular angle theta. Then what we will do later on, we are going to integrate it over all possible values of theta to find out the total energy emitted. So, as before, let us consider a plane surface AB of the black body. Let S be the area of this particular surface AB, and let us say that radiation is being emitted from AB in a direction theta. Then the energy emitted per second is going to be S cos theta into C. If U is the energy density of radiation, then the emissive power of the surface is given by E is equal to U into S cos theta into C by S, or UC cos theta. Taking all possible values of theta, that is from 0 to pi by 2, we take the average value of cos theta, and we have average cos theta is equal to pi r square by 4 integration of 0 to pi by 2, taking the solid angle 2 pi r square sin theta d theta cos theta. On solving it, this integral, and taking the limits, we get the expression 1 by 4. Therefore, E is equal to 1 by 4 UC. So, this is the relation between E and U for diffuse radiation. We have calculated the energy of the emitted radiation. Now, let us do the reverse thing. What if this black body radiation is incident on a surface? Then what is the pressure exerted by this radiation? So, we say the electromagnetic waves transport momentum as well as energy. When this momentum is absorbed by a surface, the pressure is exerted on it. This pressure is referred to as the radiation pressure. So, let us consider a photon of energy h nu moving with the velocity of light c. Let it be incident on a surface of body along the normal. From Einstein's theory of relativity, if we are considering photons, which is a relativistic particle, then the energy E is given to be mc square, or m is equal to E by c square. For a photon, the energy is given by h nu, so m is equal to h nu by c square. Thus, the momentum of the photon, which is represented by m into c, we are taking c here and not velocity, because photon is a special particle whose rest mass is 0 and which travels with the velocity of light. So, we substitute the value of m in the above expression and we get p is equal to h nu by c square into c, or h nu by c. The h nu is energy of the photon, so we have epsilon by c. Then we can say that the total momentum incident on the surface along the normal is given by p is equal to summation epsilon by c. C is a constant, can be taken outside the summation sign, and summation epsilon is going to give me the total energy E. If small u is the energy density, that is the energy per unit volume, then the total energy incident on a surface of area S in unit time along with the normal is given by E1 is equal to USC. I have explained the dimensionality that is maintained if we use E is equal to USC. Thus, the energy flux or the radiation per unit area is going to be E equal to E1 by S. Thus, E is equal to USC by S or UC. The rate of momentum transfer per unit area P is given by E by C. What is E? E is UC. So, we get UC by C is equal to U. So, rate of momentum transfer per unit area P is equal to U. Now, understand from Newton's second law, rate of momentum, which is nothing but force. Force per unit area is nothing but pressure. So, effectively this P represents not only the rate of momentum transfer per unit area, it also denotes the pressure exerted by the radiation. So, we have seen that because the rate of momentum transfer is force and force per unit area is pressure, thus the radiation pressure is equal to U for normal radiation. In words, we can say that for normal incidence, the radiation pressure is equal to the energy density U. We can also show that for diffuse radiation, pressure is U by 3. By diffuse radiation, I mean if the pressure radiation is falling on the surface at all possible angles, as shown in this figure. Here we have the surface QR, light is incident on the surface. Now, this light represented by this arrow rays are incident at all possible angles. Here we are taking only one angle equal to theta, but this theta can take any values. So, we integrate and get the proper value of the pressure. So, we have calculated the pressure, we have calculated the energy emitted. Now, let me move on to a very important law of black body radiation called the Kirchhoff's law. In the course of these lectures based on radiation, we will be discussing various laws like the Kirchhoff's law, the Stephen-Boltzmann law, the Rayleigh-Jeans law, the Newton's law, and most importantly the Planck's law. Planck's law is a universal law and is most important. All the laws are contained in Kirchhoff's law, in Planck's law. So, what is Kirchhoff's law? At a given temperature and for a given wavelength, the ratio of the spectral emissive power to the spectral absorptive power for all bodies is a constant and is equal to the spectral emissive power of a perfect black body E lambda at the same temperature and for the same wavelength. So, remember this ratio E lambda by A lambda will be equal to the emissive power of a perfect black body represented by symbol capital E, provided that all the three are at the same wavelength and at the same temperature. When I say at the same temperature, it means the black body chamber is maintained at the same temperature, and then we can see that Kirchhoff's law holds valid. This law also means E lambda is proportional to A lambda, which gives a very important result that good emitters are good absorbers. So, black body is a good absorber, so it has to be a good emitter. Therefore, we can say that Kirchhoff's law implies that at a particular temperature, a body can absorb only those wavelengths which it is capable of emitting. So, that shows the color of the black body. To derive the Kirchhoff's law, let us take Q to be the quantity of heat radiation incident on a body in 1 second. Now, out of this Q, if Q1 be the amount of radiation absorbed by the body and E lambda d lambda be the amount of heat energy radiated by the body in 1 second per unit area at temperature T and wavelength lambda. Then the total energy given out by the body will be equal to Q minus Q1 plus E lambda d lambda Q is equal to Q minus Q1 plus E lambda d lambda. Also we have A lambda is equal to Q1 by Q, which simplifying further gives me Q1 is equal to A lambda Q. Thus we have Q is equal to Q minus A lambda Q plus E lambda d lambda. Q gets cancelled on both the sides and we are left with E lambda d lambda is equal to A lambda Q, which would mean that E lambda by A lambda is equal to Q by d lambda, which is going to be equal to Q, a constant. Let this equation be called 1. For a perfect black body, E lambda is equal to capital E lambda and A lambda is equal to 1. Thus we have E lambda by 1 is equal to Q by d lambda. Call this equation 2. Comparing 1 and 2, we get E lambda by A lambda is equal to capital E lambda is equal to constant, which is nothing but the Kirchhoff's law. Let me illustrate the Kirchhoff's law by discussing a few examples. What does the Kirchhoff's law mean once? If the emissive power of a body is greater, according to Kirchhoff's law, the corresponding absorptive power also must be greater. That is, from Kirchhoff's law, it follows that good absorbers of radiation are also good emitters of radiation. When a polished metal ball having a black spot on its surface is heated to a high temperature, then to illustrate the Kirchhoff's law, the importance of Kirchhoff's law, the applications of Kirchhoff's law, we see that the black spot shines more brightly than the polished surface. This is due to the fact that the black spot is a better absorber of radiations and hence accordingly it will be a better emitter. This is a direct consequence of the Kirchhoff's law. Similarly, when a green glass plate is heated in a furnace, it appears red. This is because at ordinary temperatures, green glass absorbs red strongly and emits green. At higher temperatures, it emits red. So I hope you have understood in today's lecture what is Kirchhoff's law, what is the pressure exerted by black body radiation, what is the energy emitted by a black body radiation. The further topics will be discussed in detail in my next lectures, so stay tuned. Goodbye.